So today what we're going to talk about, now that we've organized all of our information, we're going to look at summarizing it with numbers, numerically. And remember, we talked about a distribution where we took a number line, and above the number line we made those dots. Remember doing that? And those dots, if we trace to the top dot on each column, is going to form some sort of a curve like this. And I drew this intentionally to be a bell curve because in nature, data information tends to fall in a bell curve. If you look at the heights of people, there's a lot of people that are about the same height right in the middle, but as you get really short, there's very few people. If you get really tall, there's very few people that are that height. Your scores on a test, if it's a well-written test, should look like this. A lot of people in the middle, very few with really high, very few with really low scores. And the technical name for this is called a normal curve, or normal distribution, because that's the shape that data in nature normally takes. Now there's two things we need to describe here, and I think we mentioned this before, but I'm going to go over it again quickly. One is center. Like for example, this one here, there's the center of the curve. But I can draw a nearly identical curve the black curve and the blue curve look about the same, only the blue curve is shifted to the right. It's changed its center. It has a different center. So that's one of the things we're going to talk about, is how do you measure the center of one of these curves, of the distribution. The next is something we call spread. You look at that one's fairly wide. But when you look at this green curve, has the exact same center as our black curve, but you can see it is much less spread out. It's narrower. And that width or narrowness is called the spread, sometimes called dispersion. And that's what our main focus is going to be today, is measures of center and spread. So what I'm going to do is we're going to take a small set of numbers, and we're going to find our measures of center and spread. In fact, what we're going to do is we're going to do two sets of numbers, just because there are some slight differences. So I'm going to split my page right down the middle. My first set of number is going to be right there. My second set of numbers is right there. So this is going to allow me to do two examples of each type. So my first measure of center is something called a mean. The mean is what we've all been trained to call the average. Probably around 3rd or 4th grade we did the average of things. Now one thing we should define, N. N is the number of items in a list. So for this set here, N equals how many? 5. And over here, N equals 6. There's 6 items in the list. The mean, the average, is found by adding the numbers up and dividing by how many are there. So over here, we're going to do 7 plus 18 plus 11 plus 13 plus 21. Divided by 5, divided by N. So that's what, 25, 36, 49, 70 over 5 is 14 is the mean. Does that look right? Okay. Over here, we do 12 plus 21 plus 16 plus 15 plus 23 plus 18. Divided by 6, because there's 6 of them. So 33, 49, 64, 87, 95, 105 divided by 6, which is 17.5.
Yep.
Okay. So we've got the mean of each data set. Does that make sense how we find the mean? Our second measure of center is something called the median. The median is the middle number. Now to find the median, we first must put the numbers in order from smallest to largest. So this first data set, we're going to do 7, 11, 13, 18, 21. Second thing we must do for the median, so that's step 1, is put them in order from smallest to largest. Step 2 is find the position of the median. So what we're actually going to do is we're going to calculate how many numbers must be smaller than the median. And what we do there is we take 1/2 times n, or 0.5 times n, whichever is easiest for you. So in this case, that's going to be, I'm going to do 0.5 times 5, because n is 5, right? That gives us 2.5. What this is telling us is that there's 2.5 numbers in this list smaller than our median. So when this comes out to be a 0.5, you round up. 2.5 rounds up to 3. The number in the third position is our median. What's the number in the third position? 1, 2, 3. If I label them all up, 13 is the third number in the list. 13 is our median. It's in the middle of the numbers. So let's try that over here. So I've got 12 as my smallest. Looks like 15, 16, 18, 21, and 23, correct? So now I'm going to take 0.5 times 6 is n, right? Gives me 3. What that's telling me is that there's 3 numbers smaller than my median. If the number here when it came out to be 0.5, we rounded up. If it comes out to be a whole number, in other words, no decimal, then it's between that one and the next. So that's saying is it's between the third and fourth number in the list. So 1, 2, 3, 4, 5, 6. It's between the third and fourth number in the list. So how do we find it? We're going to take those two numbers, 16 and 18, add them together and divide by 2. So 16 plus 18 is 34. If you're doing this on your calculator, make sure you hit equals before you divide. 16 plus 18 is 34, divided by 2 is 17 is the median. You'll notice in both cases here, we had a mean of 14, a median of 13. They're pretty close. Mean is 17.5, median is 17. Pretty close. The mean and the median, if the data is really in a perfect bell curve, the mean and the median should be exactly the same. But since data usually isn't perfect, they should be close to each other. The next one is something called the mode. The mode is the number that occurs most often. In both of the lists I gave you, there's no number that appears more than once, is there? There is no mode. And most small sets of data, I mean, 5 and n equals 5 and n equals 6 are both pretty small sets of data. In small sets of data, there's a good chance there isn't going to be a mode. Usually you have to get a lot larger. So if I had something like, and I'm just going to put these in order. Here, obviously, there's a mode of 18. What if there's more than one number that appears twice? Well, depending on what, statistics is not set in stone. There's different views and different things in statistics. This is one of them, or different schools of thought. Some textbooks will tell you can have up to 2 modes. Some textbooks go through some fancy formula if it's the square root of n minus whatever. If you have a really big set, you can have like 5 or 6. You can be multimodal. You can have 5 or 6. For our class, either it has one mode or it has no mode at all. Next, there's something called the mid-range. The mid-range is found by taking the minimum, which is the smallest number, the maximum, which is the largest number, and then dividing them by 2. Adding them together and dividing by 2. So for our first set here, we have 7 and 21. So 7 plus 21 divided by 2. Well, 7 plus 21 is 28. Divided by 2 is 14. Again, right along with our mean and our median. Over on the second set, we had 12 and 8. Sorry, not 12 and 18. We had 12 and 23. 12 plus 23 is 35. Divided by 2 is 17.5. That's actually the same as our mean. So you can see the measures of center in a perfect set of data should all be the same, or in a good set of data should all be really, really close. If your mean and your median are really far apart when you find them, that's telling you that your set of data is probably a really ugly set of data. So before we move on from this, the question I'm going to pose to you is, which is better? Now, I've probably already kind of slipped on my opinion of the mode. Mode's not horribly useful. It's really quick, but not necessarily a good measure of center. Mid-range is quick as well, but not great. So it really comes down to the mean or the median. Well, what do you guys think? Which one do you think is better, mean or median? Mean. Most people go with the mean because you got a formula. You're putting the numbers in, you're adding them up, you're dividing, you're cranking out a. I felt the same way. But let me show you an example here. This is also my way of getting you to do an example in your notes, by the way. So for this list of numbers, let's see here. Find the mean and the median. So what'd you get for the mean? 27. Perfect. How about the median? 27. So they come out to be exactly the same here. Now I'm going to mess with you just a little bit. I'm going to add this number. Oh, what did that add up to? That added up to 110, didn't it? 135. Okay, sorry. Let's do that. Let's add 105 to it. If we add 105 to it, what is the new mean? What is the median? Oh, I can't write today. You're adding them all up, right? I'm dividing by 6 now. If you add them all up, it comes up to 240 divided by 6, which gives you a mean of 80. Is that what you come up with? Need a second yet? What's that? 40, I'm sorry. I don't know where I came up with 80. 40, you're very, very right. 40. So then, median. 0.5 times 6 is 3, so that means it's between the third and fourth, right? Which means it's between 27 and 28, which gives us 27.5. What I did here is I put in one really large number, and it could be the same way with a really small number. It would do the same thing. When I put in that really large number, what did it do to the median? Really jacked it up. the mean, I should say. Now the mean is, there's only one number larger than the mean. There's 5 that are smaller. Not necessarily a good measure of the center, is it? It's not really in the center of the data. Down here, 27, the median went from 27 to 27.5. Still has half the numbers smaller and half the numbers larger. It's still in the middle. The median is commonly accepted to be the better measure of center. It's more stable is the big thing. Now, I'm going to show you an example of how this has been used in the past. In 1983, University of Virginia published that the average starting salary of a graduate in their bachelor's, their BS marketing program was just under $78,000 per year. Now, first of all, right now you're thinking $78,000 a year starting salary is pretty good. Think back to 1983. In 1983, which most of you, none of you were born yet, I don't believe. In 1983, average high school teacher was starting out between $16,000 and $18,000. So $78,000 was incredible. There's a problem with that, though. In 1983, one of the students who graduated from University of Virginia with a degree in marketing was a man by the name of Ralph Sampson. Now, I don't know if anybody in here is a huge NBA fan or a huge basketball fan, but Mr. Sampson was 7'4", was 3-time NCAA Basketball Player of the Year, sophomore, junior, and senior years. Drafted #1, first overall by the Houston Rockets. Anybody want to guess how much money he made that year? Millions, several millions. Even if it was just $1 million, it takes a lot of $20,000 marketing students to average $1 million down to $78,000. As we saw up here, that one high number can really change the mean. Well, throwing a number that's $1 million, it really throws things out of proportion. Mr. Sampson was the only person in that group that made more than $33,000 that year. The median of that group, this was the mean. The median was about between 22 and 23,000. Still not bad, but not nearly as impressive as 78,000. Was this an actual, real, legitimate statistic? Yeah, it is. Is it honest? It's twisted. It's ethical. Unethical, I would say. And that's, I could go on, and it's a big issue for me in statistics, is ethics in statistics, honesty in reporting. It's just huge. There's so many ways. You've heard that you can make the numbers tell you anything you want them to. Well, there's a lot of truth in that, depending on how you organize them, how you eliminate numbers. And there's something called outliers. An outlier is a number that's way different from the rest. Now, in this case, Mr. Sampson's contract would have been an outlier. It's way bigger than all the others. When you deal with outliers, you have to decide, is this a real piece of data, or is it one that, even if it is a real piece of data, is it one that should be eliminated? In this case, his income had nothing to do with being a marketing student, so it should have been eliminated from the data set, ethically speaking. There are other cases where you get an outlier where you look at it and you can't confirm it. So it might be like if you're measuring weights of things or whatever, it might be that the scale malfunctioned or something like that. It might be an error in measurement. So you eliminate it because you can't confirm that it's a real data point. There are other times where the outlier should stay in there. If you're finding the average height of students or average height of children, if you got a student or child who's really tall or one who's really short, they should stay there. Those are real data sets and they are legitimate. I mean, their height is still based, they're still the right age. It's not like you're throwing in a 7-year-old with a bunch of 13-year-olds. Then you would want to throw their height out. Statistics is used a lot in the medical fields. When they do drug testing in medical trials and stuff like that, when they're testing new procedures and stuff, there are people that will die during the testing process. You know, for example, let's say that they're testing a new surgery and you have someone who passes away during the surgery. Well, they have to determine the cause of death, because if the cause of death is not what they were doing the surgery for, let's say they're doing a surgery to replace a hip and the person dies of a heart attack. Well, the death really, I mean, yeah, maybe the stress from being in surgery caused the death, but it wasn't a malfunction of the surgery itself. It was a side effect. Or maybe you have someone who's in a cancer treatment study and they die of a heart attack. Well, again, they didn't die because the cancer treatment failed. They died of something unrelated. So you have to decide whether you eliminate them from the study or keep them in. If you ever look at a real statistical study, at the end of the study in the appendices, there will be lists of people or whatever, the items that were eliminated from the study, an explanation for each of them as to why. And then if it's a medical study, the medical evidence is to proving that this death was not related to the medicine being given or whatever. The heart attack one's a tough example because it's hard to prove the cause of a heart attack. It could have been the medicine that caused the heart attack. Who knows? But anyway, those are our measures of center. So now the other thing we wanted to talk about was measures of spread. So I'm going to give you a set of data. And yes, I know this set is pretty lame. But it is a set of data. For our first measure of spread, we can talk about range. Now we already used the mid-range as a measure of center. The range itself is just from the minimum to the maximum minus the minimum. So for this set of data, it's going to be 28 is the largest minus 8 is the smallest. That gives us a range of 20. Here's our problem. I can construct a set of data here. Would you say that one is more or less spread out than this one? Less, because the numbers are concentrated in the center here. But what's the range of this one? Yeah, the range is going to be just 28 minus 8 is still 20. So we get the same range. So there needs to be a better way than the range of distinguishing between these, because the range just cannot give us a difference. So there's something called the standard deviation and variance. Standard deviation and variance work together. Actually, the variance is just one step short of the standard deviation. The standard deviation is a 6-step process. So rather than giving you the formula, I'm going to give you the steps. So remember, our data set looks like that. Step 1. Find the mean. So I'm going to add these all up. Divide by 5 gives me 18 as my mean. Step 2. Subtract the mean from each value. 8 minus 18, 13 minus 18, 18 minus 18, 23 minus 18, and 28 minus 18. What is 8 minus 18? Negative 10. 13 minus 18? Negative 5. 18 minus 18? 0. 23 minus 18? 5. And 28 minus 18? 10. So that's step 2. Step 3 is to square each. Now you gotta be careful. Negative 10 squared, if you don't put it in parentheses, your calculator will try to tell you it's negative 100. That's not correct. When you square something, it is always positive. Negative 10 squared is 100. Negative 5 squared is 25. 0 squared. 0, 5 squared. 25. 10 squared. 100. Step 4. To find the sum. In other words, add up these numbers. So 100 plus 25 plus 0 plus 25 plus 100 is 250. That's all step 4 is. Step 5 is to divide by n minus 1. In this data set, n equals how many? There were 5 numbers in the data set. So n minus 1 equals 4, right? 5 minus 1 is 4. You're going to divide by 4. Gives you 62.5. That's step 5. That number right there, the 62.5, would be considered the variance. But then there's step 6. Now in step 3, we squared them. In step 6, we must square root that number. So the square root of 62.5 is 7.91. We'll go to 2 digits on our standard deviations. Unless it tells, my math lab may tell you otherwise, but if it doesn't say, you go to 2 digits. So 7.9, well, what that's saying is on average, each number is 7.91 from the mean. That's the average distance from the mean. Well, let's look at that other data set. We had 8, 17, 18, 19, and 28. In your notes, see if you can find the standard deviation of that quick. Okay, so the mean, step 1 is the mean, which is what? Still 18. Very good. Step 2, we're going to subtract from the mean. 8 minus 18 is negative 10. 17 minus 18 is negative 1. 18 minus 18 is 0. 19 minus 18 is 1. And 28 minus 18 is 10. Step 3 is to square them. Negative 10 squared is 100. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 10 squared is 100. What is step 4? Add them all up. They all add up to 202. Step 5. Divide by n minus 1, right? N is 5, so we're going to divide by 4, which gives us 50.5. That would be the variance, by the way. But we're not looking for the variance. We are looking for the standard deviation, which requires one more step, which would be the square root. Square root of 50.5 is 7.11. So you can see there is a difference. Here it was 7.91. Here it's 7.11, indicating that this data set is less spread out. Okay, so that is our measures of spread. What is all this good for? There's something called the empirical rule. What the empirical rule states is that if you have a set of data that's approximately normally distributed, there's going to be set percentages that always occur. So if we look at our bell curve, pretend I made that even, the center of the bell curve. Now it could be the mean, could be the median, could be the mode. We're going to use the mean. If you go out a distance of 1 standard deviation, 34% of the data should fall between the mean and that 1 standard deviation mark. Whether you're going below or above, if we go this way, plus 1 standard deviation above, it's still 34% between the mean and that 1 standard deviation. If you keep going, between 1 and 2 standard deviations, there'll be 13.5% of the data, no matter which direction you go. If you keep going, between 2 and 3 standard deviations, there is 2.35% of the data. Then, more than 3 standard deviations away on each side, there's only 0.15%. 0.15%, that's like 15 out of 10,000. So very unlikely. So if you have a good set of data, it's very, very unlikely that anything will be more than 3 standard deviations away from the mean. These percents always stay the same. These numbers down here, of course, can change depending on your mean and standard deviation. So what do I mean about that? Well, let's say that we're looking at the height of your average, excuse me. Let's say that we're looking at the height of your high school graduating. We're going to go with male just because there is a difference in height. Let's say the mean height is 71 inches with a standard deviation of, let's go 2 inches. I'm just throwing these out there. I have no idea how accurate they are. What that would mean on this curve, 71 goes right there. Now if I'm going to subtract 1 standard deviation, what is this number going to be? 71 minus 2 is 69. What's this number going to be? 67 and 65. Going this way, if I add the standard deviation, this will be 73, 75, and 77. So what this saying is, let's say that you are 73 inches tall. Here's 73. If you add up these percentages, you get 84%, right? That's saying 84% of high school graduates are shorter than you. Or if you add up these percentages here, you get 16%. 16% of high school graduates are taller than you. Let's say you are 67 inches tall. Well, here's 67 right here. What that's saying is only 2.5% are shorter than you. And of course, if you added up the other ones, that ends up being 97.5% are taller than you. Does that make sense?
I have a question.
Yeah.
So for that, what if you like, I'm just like putting this out there, what if you're like in the middle of those numbers?
Well, this doesn't work so well, does it?
Yeah.
Yeah, if you were at, say, 70 inches, well, then you don't know where everything falls. You know that at least 50% are taller than you, right?
Mm-hmm.
And probably about halfway through that 34%, so maybe another 17, but you don't know exactly what it is. You can find it exact using an actual normal probability instead of just, this is an approximate,
Mm-hmm.
but we're not going to get that in depth into it for this course. But yeah, there is a way you can do it using normal probability calculations. Like on my calculator here, if you want to define that, there's actually a normal calculator here. Use the normal CDF function. Then you want to go from 70 to positive infinity. Or greater than 70 is going from 70 to positive infinity. The way you do that on the calculator is enter 6 nines. With a mean of 71 and a standard deviation of 2. That gives you 0.69. So 69.14% of people would be taller than you if you were 70 inches tall.
Okay.
But like I said, we're not getting that detailed in here, but you can get you could get for 70.5 inches tall if you wanted to. You can get exact numbers for whatever you want to, but we're not going to get that in depth. Sure. Well, how could this be useful to you? Well, let's say you get out, you leave school, and you're offered a job. And the job offers a starting wage of $12.40 an hour. And you do some research, and in the area you are in, starting wage has a mean of $10.80 an hour with a standard deviation of $1.60 an hour. So is that a good wage? Well, it's better than average. It's better than the middle range, right? Remember, these percents in here always stay the same. Always. What goes down here, of course, is what changes. What goes in the middle here? 10.80, yes. What's going to go here? Perfect. Yeah, we subtract the 160. We subtract standard deviation. So 920, 760, and $6. Obviously below minimum wage, but yes, there are jobs that offer below minimum wage. You can allowed to pay. Some states actually have a juvenile minimum wage where you can go below regular minimum wage for people under 18, or training wages and stuff like that. Going this way, of course, you have 1240, 14, and 1560. You fall right here. You're going to be getting paid more. If you add those up, you're getting paid better than 84% of people starting. So only 16% of jobs in that area offer a better starting pay than what you're going for. So it means it's a pretty good starting pay, and you've probably picked the right career choice, right? Or another side of it might be this. You're going to move. You took that job and you're going to move to this new city. And you want to buy a house. Well, of course, when you move to somewhere new, the price ranges, home prices are one of the things that varies the most from one area to another. I mean, even in Barron County here, going from Rice Lake to Barron, there's a huge difference in home prices. So you do some research. You find a house. You're going to look for 3-bedroom, 2-bathroom houses. That's what you really want. And you're looking and you find one that you absolutely love. The price on it is, oh, what do I want to do? $148,000. Well, you do some research in that area. For 3-bedroom, 2-bathroom houses, the mean is $112,000. The standard deviation of $18,000. So let's draw our curve. So 34 and 34, 13.5, 13.5. Got our percents in there, right? What goes in the middle? 112,000. I'm just going to put 112. So subtracting 18, this would be 96, 78, and 60. This would be 130, 148, and 166, right? Your $148,000 house is right here. If I add up these numbers here, 97.5%. What that's telling you is that 97.5% of all 3-bedroom, 2-bath houses in that area are cheaper than what you're looking at. So even though you may love this house, there's a pretty good chance you're going to find one cheaper that you still like. Does that make sense? So this is a very powerful rule. I think that's, well, actually I do want to kind of squeeze this in a little bit quick. We might be a little late on our break today. Now you asked the question, what happens if things are in between there? Now, I showed you briefly that exact normal probability, but I'm going to show you something else where you don't have to be exactly on a standard deviation. But what this involves is comparing two populations. We talked about a population as being a group you want to learn about. Well, sometimes, even though they're the same population, there might be reasons why you'd split them. For example, if you're going to looking for a job in Rice Lake versus looking for a job in the Twin Cities, Minneapolis, St. Paul area. Let's say you're going to be offered $11 an hour in Rice Lake and $14 an hour in Minneapolis, St. Paul. And you're thinking, hey, $3 an hour more. I'm just going to move out there. Well, how do you compare? $13 an hour there is not the same as $13 an hour here, because cost of living and all that. People just plain get paid more out there. Well, how would you compare? Let's say you get an offer. We're just going to call it offer A, which is $12 per hour. Offer B, which is $16 per hour. And you're thinking, geez, $4 an hour more, that sure looks good. But if we're looking in the area where offer A is from, the mean starting salary, or starting wage, I should say, is $10.80 per hour. The standard deviation of $1.80 per hour. In the area where offer B is from, the mean starting wage is $13 per hour. Now you're looking at that thinking, wow, that's $3 an hour more. With a standard deviation of $3.20 per hour. Well, there's something called a z-score. And a z-score is used for comparing items from two different populations. It's sometimes called standardizing a piece of data. So what a z-score is you take a number and you subtract its mean, the mean from the population it comes from, then you divide that difference by the standard deviation. So for the first one here, your z-score is found by taking the number, which is 12. You're going to subtract the mean, which is 1080, and divide by the standard deviation of $1.80. So we're going to subtract 12 minus 1080 is $1.20. Divided by $1.80 is 0.67. What that is saying is that this $12 an hour is 0.67 standard deviations above the mean for that population. So how about over here? Let's see how it stacks up. So we've got 16 minus 13 over 320. Well, 16 minus 13 is 3 over 320. 0.94. So that's saying that's 0.94 standard deviations above the mean. So this one does turn out to be the better wage. Make sense? Just because it is more standard deviations above the mean. All of you had to take entrance tests to get into school. And I know technically they call it communications and math, but we're going to call it English and math. Let's say on your English test, you scored a 28. And on your math test, you score 24. Thinking, does that mean you're better at English than you are at math? Well, not necessarily. Let's say that for all students who took the English test, there was a mean score of 22. The standard deviation of 3. So for all students who took the math test, there's a mean score of 19, with a standard deviation of 2. But you're still, this is 6 points above the mean. This is only 5 points above the mean. Still looks better. But let's do the z-score. So z here is going to be your score of 28 minus the mean of 22. That's going to be divided by 3. Well, 28 divided by 22 is 6. Divided by 3 is 2. You scored 2 standard deviations above the mean. Now we can go back to that empirical curve, the bell curve, and find a probability. Technically, you scored better than 97.5% of all people that took that test. Over here, however, your z-score is going to be 24 minus 19 divided by 2. 24 minus 19 is 5 divided by 2 is 2.5. You're 2.5 standard deviations above the mean. You technically did better in the math test. Okay, we're a little late on our break, so let's take our break. It's 9:23. We'll come back at 10:23.